And we might break this up into small pieces if possible too, because there's sections to this part. So yeah, I wouldn't be opposed to doing like a couple different techniques and then letting you work on those a little bit and then coming back, and that's fine. If it falls at the right time, that's great. So factoring polynomial expressions. Now we've already done some of this, right? Let's review what we did. Okay, we did stuff like we were able to factor trinomials, right? And this was a hard one. This was one of the ones where a was not equal to 1. And we had to do that whole process with the a times c then split b stuff, right? And it's been a while since you've done that, but this will be our opportunity to actually review that a little bit too, in case you forgot. So that was the hardest part of it. We did that. Perfect square trinomials, we just dealt with those like normal trinomials, and that's fine. We can continue to do that. Difference of squares, remember, those were easier. If we could think of something as being a squared minus b squared, then it factored really easily into a plus b times a minus b. And then we always want to factor out we call it the greatest common factors, how we refer to it. So in this case, if I had 6x squared plus 15x, let's see, 3 goes into both 6 and 15, right? And both of those have an x that I could divide away. So I could pull out the greatest common factor in this case, 3x. I could undistribute that or factor it out, and I'd be left with 2x plus 5. And so that stuff you guys are all good at, or with a little bit of review can be good at again very quickly. Okay, so that's what we know. This stuff all applies, you'll notice, to quadratics though. Quadratic functions, which are polynomials, right? We're going to deal with bigger polynomials now. Okay, so I'm not going to mess with this graphic for now. There's kind of a cool geometric way that you can show how this works, but it doesn't really help you do the problems. Let's kind of focus on the pragmatic part of it for now. So if I skip through this, and let's just get down to the answer. So here's what we get for a formula then. When we're factoring stuff, okay? Here's one of the factoring patterns that we're going to add to the patterns we already know. We already have one of them. When we're dealing with quadratics instead of cubics, there's only one factoring pattern, and that was a difference of squares, right? If I have something squared minus something else squared, what was that factoring pattern? A squared minus b squared factored into, okay, good. So a plus b times a minus b, right? Okay, and that was our conjugate pattern. And that's the same thing we looked at in 6.3, going the other way. If I multiply two conjugates together, then I know that I end up with a difference of squares. So that goes both ways, of course. Now, this is important to also recognize the other potential factoring pattern for quadratics, for second degree polynomials. A squared plus b squared does not factor. Okay? So if we get something like that, for example, if you were asked to factor 2x squared plus 8, you'd know right away, don't even try. You can't factor that. I could factor a 2 out of that one, I guess. Let me pick a better constant. What if we pick 7? You can't factor that because it's a sum of a term. We could think of that as being something squared maybe, right? And that is being something squared. But a sum of squares, there's no pattern. It will never factor. So only when you get something that looks like, instead of that, oops, only if we got something, we didn't mean to do that. Only if we got something like this. Say we had 16x squared minus 100. Now that we could do, right? I could write that as, this would be like saying 4x squared, right, minus 10 squared. Okay, and then that fits the pattern. That's my A and that's my B. And so it'd be 4x plus 10 times 4x minus 10. that works. But if that were a plus instead of a minus, don't even try. It's never going to factor. Okay. Okay, so we get this first pattern, a sum of two cubes, and then we get the other pattern, which is a difference of two cubes. Okay. Now I'm not just going to brush through those. Let's talk about those, and I'll show you kind of a trick for maybe memory, because you need to memorize these. You need to know these. There's very few things in algebra you got to know. The factoring patterns are some of it. We're going to use these a ton, and you're just going to need to know them. So let's look at those in a little more detail. Okay, let's start easy. So we've got the one we already know, a squared minus b squared. What's that equal again?
C squared.
No.
A plus b times a minus c.
Good. A plus b, a minus b. Good. And now we got the new ones. Now we got the patterns for cubes. Thank you. No Taylor today? Oops.
There's Sally.
Yeah, not here.
There's Sally.
Okay, so now we got the other patterns. The sum of cubes and a difference of cubes. A cubed plus b cubed. Here's how you can remember these. Real simple. They're going to factor into two factors. I'm going to get a small one and a big one. Okay? The first one is going to be whatever the two, A and B are. Those are the two players, the two terms in the first factor. Okay? A is the first factor, B is the second factor. So let's have all phones and stuff away from this. In the second one, over here, we're going to get three terms, and they're going to be, one of them is going to be a squared. They're all going to multiply to a power of 2. In the first case, all the power is with the a. The middle one is going to be a to the 1 times b to the 1. The exponent still adds to 2, though, right? And then the third one is going to be the b squared. Okay, just like that's real similar to that Pascal's triangle thing we were looking at, and the expansions we've been working with also. Okay, now what signs go where though? This is the part that can be a little tricky. Okay, whatever the sign is here, that becomes the sign there. Okay, so the first plus sign matches up with the first plus sign. Whoops. Okay, then whatever this one is, we're going to do the, whoops, gosh darn it. We're going to do the opposite. So, and that's going to be a minus. Okay. And then the third one is always plus. Okay, and if you know that one, the same rules apply to the difference of cubes. So what's the difference of cubes going to look like then, do you suppose? If I have a cubed minus b cubed, get small and big, right? I get the same terms in the factors. I'm going to get an a and a b, and in the big one I get a squared, a times b, b squared. But what are the signs going to be?
Minus plus.
Yeah, it's going to be minus, plus, plus. Okay? And otherwise, this is just kind of plug and chug. It's very simple. Once you know what the pattern is, you just follow the pattern, and that's it. So let's try an example. So there are our patterns. Okay, let's try this. So say we want to do x cubed. We'll start simple. X cubed plus 27. Now, first of all, we have to identify which pattern is this. We got 4 choices, right? It could be, our 4 choices are sum of squares, difference of squares, sum of cubes, difference of cubes, and remember that sum of squares doesn't work. So if that's the pattern it would fit, it doesn't factor and we're done. So which of those patterns would this one fit? We got our choices. And I'm going to write this down. Yeah, this is kind of important. If you can get this part, sort of the strategic thinking about this, then the rest is a lot easier. So here are our choices. A squared plus b squared, which is not a pattern anyway. squared minus b squared, a cubed plus b cubed, a cubed minus b cubed. Yeah, does that make sense? Why? What's your thinking there? Why is this clearly the winner? X is cubed, right? X is cubed. You want to look at the exponent. That's the key, right? X is being cubed, and so it's got to match this pattern, if any of them. And so then the question is, what's our A and what's our B?
X is A, 27 is B.
Okay, but X is A,
A's 1.
so I can write this as something cubed plus something cubed, and X is the first something, but what's the second something going to be? 3, good, because the cube root of 27 is 3, right? So we get x cubed plus 3 cubed, and then all we have to do is follow that pattern, right? Okay, so let's watch it in action. Okay, so there's our x cubed plus 3 cubed, and then if we just follow, remember our pattern, a plus b times a squared minus ab. ab is just going to be x times 3, which we'd write as 3x, right? Plus b squared, b is 3, right? See how that works? Okay, just follow the pattern. Okay, should we see that one again?
Why did you have to go and put the x cubed plus 3 cubed down in this weird other thing?
Okay, let me write it on another page, because I think that's important to do. I think it's important to do, because,
Really confused.
okay, well, let me,
I understand that you have the x cubed plus 3 cubed, I get that. But then why are we putting it in this other form?
in this form right here.
Yeah.
Oh, because that's our job. Our job here is to break this thing up into factors. And you might ask, why are we doing that? Yeah, that's a good question.
Okay, so the x cubed and 3 cubed are part of the factoring of x cubed plus 27?
Let me hold that thought. Let's do the same problem from a slightly different perspective, so we'll get a little different view on this thing. Okay, so first of all, why do this? Why factor in the first place? Well, what if I've got x cubed plus 27 equals 0 is the equation that we're trying to solve?
Why couldn't we just minus 27 and divide by the square root?
Well, you can't square root it. Okay,
But then
and
you just get I.
you're right. You're right. You can, and that's something we're gonna learn. And remember, that's a shortcut. This is gonna follow exactly parallel to what we did in chapter 5. Remember in chapter 5 how that worked. In chapter 5, we said, what if we have something like x squared minus 9 equals 0, right? Now, everybody paid close attention to this, because this is, if you really follow this, you'll get the structure of this chapter, and it really helps. This is the way to learn it, though, I promise you. What we said first was, okay, we learned that we could break this up into a difference of squares, factor it that way, and then solve by the zero product property. Set the factors equal to 0, right? So we got the answers either x equals -3 or x equals 3. But then we came along and said, aha, there's a shortcut to this. Okay, there's a shortcut here, and the shortcut is we could just say if x squared minus 9 equals 0, let's just isolate x. That was our 5.3 great trick that we learned. We can point to a single x, and so therefore we can isolate it. So we just add 9 to both sides, we square root, and we get x equals plus or minus the square root of 9, which is 3, right? Now we are going to learn a corresponding shortcut in the future, not even in this chapter, for dealing with other kinds of roots. So we are going to learn that we could subtract 27 and take a cube root. But there's a little more to it than that. When you're taking higher order roots, there are some rules that go with it that complicate things a bit. And it really takes some time to go through those. And so, and this process, by the way, this process also, though, is just as valuable and just as quick, because sometimes we need the other factor from this also. And you'll see why soon. So let's ignore this other process, this other shortcut for now. We will learn it. In certain cases, when we're only looking for real solutions, it's a great shortcut. If we're looking for all the solutions, including the imaginary solutions, it doesn't help us. Okay, so we're back to this stuff. So what do? Right? We gotta factor this thing so we can set the factors equal to 0 to find all the solutions. Right? So we gotta break this thing into pieces. So what are those pieces gonna be? Well, we'll just follow our pattern, right? It's gonna look like that. Okay, can we make this thing look like something cubed plus something cubed? Because if we can, we have a pattern for that. And remember what our pattern is. A cubed plus B cubed equals, once again, see if you got it memorized.
A plus B.
A plus B.
A squared minus AB plus B.
Okay, good. So can we find an A and a B? Yeah, you already told me. A is X in this case, and B is 3, right? And that looks like then A cubed plus B cubed. So we're just going to follow that pattern. X plus 3 times X squared minus 3 times X. Technically, if we do this, if we just follow strictly a pattern, A is X, isn't it? So we're really saying X times 3 plus 3 squared. What does that all equal, though? Well, that's just going to be X minus 3 times X squared minus 3X plus 9 equals 0, right? So we got it factored, okay? Now, if we want to find the answers, we just set each of these factors equal to 0 and solve. So I'm going to get the two equations, either X minus 3 equals 0, or X squared minus 3X plus 9 equals 0, okay? Okay, so is everybody with me? This is huge. I don't want to say this 1,000 times. I want everybody to just focus. Everybody with me? Take a second. Stand up if you need to. Walk around your desk. Okay? No takers? All right. So now we got to find the answers to these both. First one is simple. What do we get? X equals 3. Okay? For the second one, now this takes us back to chapter 5. Okay? Chapter 5. Now if I'm solving a simple quadratic equation like that, I can't isolate X, right? Because I've got X squareds and X's, so I've only got two choices, either factor or quadratic formula, right? Are there two numbers that multiply to positive 9 and add to negative 3? No, so we got to use quadratic formula. Now watch this closely, because there's something that's going to happen here that's going to be the same result every time. This is big. So if I solve the quadratic formula, I get X equals negative B, so 3 plus or minus square root B squared. So what do I put in there for B?
3.
Positive 3, right? Never square negative. 3 squared minus 4 times 1 times 9, all divided by 2a, so divided by 2, right? Okay? Yeah, but a's 1, right? Okay? So if we simplify that then, X equals 3 plus or minus, well, what's this all going to be? If we just do the math here, I'm going to get 9 minus 36, so negative 27. Everybody agree?
Yeah.
So I'm going to get the square root of negative 27, all divided by 2. Okay, so what's that look like? Oh, not a room. I got to go to the next page. I'm not quite finished with this. Uh-oh.
That's just not real.
Does it?
Not bad. It's a little blue mark, see it? Can you stand
Yeah,
it?
but I should be able to do.
Oh, goodness.
I think this pen is actually, I think it is getting a little bit tired.
You broke it.
There we go.
I want one of these.
Don't you? That'd be great. Think how awesome it would be in college when you're doing
Call of Duty.
Oh gosh. Okay, so let's get this down in a couple answers. So I get X equals 3 plus or minus The square root of negative 27. What do we do with the square root of negative 1 part of that? I. Okay, so we're going to get an I from that, aren't we? And then I'm going to get the square root of 27, which I could break into square root of 9 times square root of 3, if I want to be tricky. So I could write that as times 3 radical 3, all divided by 2. Okay, and that's an okay answer, but if I break this up into a complex number in standard form, that looks like 3/2 plus or minus 3 times the square root of 3 over 2 I. Okay? Two important things just happened there that I want you to recognize. First of all, when we solved this quadratic equation, we haven't made much of a mention of this, but in chapter 6 we start to get real intrigued by this idea. That when I get two imaginary solutions like this from the quadratic formula, notice that they are complex conjugates. The two of them are, it looks like A plus B times I or A minus B times I, right? So they're always going to be that way. I'm going to get two partners in crime, two complex conjugates for my imaginary solutions. Was it an accident that I got I's in both of my other solutions to this cubic polynomial that we were solving? No, not at all. It's always going to be that way. Whenever you do this factoring pattern, this guy right here, and everybody hear this, this is big. Whenever you do this factoring pattern, a cubed plus b cubed, so a sum of cubes, or we're going to find a difference of cubes, the little guy out in front is always going to be real every time. It's going to give you back x equals a number. You know, it could be different every time. That's always going to be real. The two solutions that you get from the big quadratic factor are always going to be imaginary, every time. And so you can take a big shortcut here. If the question is only asking you to find the real solutions, then all you have to do is focus on that first one. Forget the second one. If you need them all, then you're going to have to, find the zeros of the second one, probably with the quadratic formula. Okay? Make sense? Okay? It's going to be that way every time. Now, what we call that is, and this is an example of it, every time we get one of those, it is an irreducible quadratic. Meaning you can't factor it into real, it's never going to factor. You're always stuck with that. Okay? So it's a quadratic factor that cannot be broken any smaller, and we'll come back to that idea. So we got our answer. Okay? That's it. Long story short. Okay, let's look at another one. And this would be a good place for us. If we can get through this today, this is great. This would be plenty. Okay, what about this one? Maybe there's some stuff we can do.Maybe. But let's put this on a bigger... Yeah, you can't see that very well, can you?
16, is that
Can you see
M?
that in the back? Is that?
Yep.
Okay.
16u5
Oh, it's a
minus
U.
16u to the fifth minus 250u squared.
Get your eyes checked. I love my glasses, that's right.
Okay, so move up the after. So we're in factoring mode here. If I want to factor that thing, we got to kind of go through our checklist of factoring. What do we always do first when we're trying to factor something? It's been a while. Go back to chapter 5. What do we always try to do first?
Reduce.
Well, sure. But we want to always see if we can factor out a greatest common factor. Can I divide something away from each term? Because that always makes life good for us in the factoring sense.
Can you get rid of the u2?
Yes, we
So
can.
that it's
The u squared. We
u
can. We could factor out a u squared. Because I can both these terms, I could divide a u squared away from each term. That's great. Now, that's great. What about the numbers? Is there a common numerical factor? Well, there's got to be at least one, obviously.
2.
2 goes into both of those, right? And that might be it. I think that's it. So I could factor out a 2u squared, right? And factor out greatest common factor and get that. 2u squared times 8u cubed minus 125. Now from there, I want to do this on my own terms. I don't want to follow this PowerPoint.
I'm very confused. How do we get this big long answer from that tiny thing?
You'll see.
Somehow we get that.
We'll see here. So
I bet Albert Einstein struggles through this.
I bet he could too.
Yeah, he probably created it.
Okay, so we're okay with that? Okay, we got that because we're just we're asking the question, what can I divide out of each of these? Okay, I need, quiet. We can't get side stuff going on. Everybody's got to be focused up here. So I can take out a u squared, divide that away from both of those. Right? And what have we done there? All I'm saying is if I want to factoring out a u squared or a 2u squared is like dividing each of these terms by that. Okay, so if I take 16 u to the 5th divided by 2u squared, what is that? 16 over 2 is 8. And then, right, u to the 3rd by our properties of exponents. Oops, not 3 to the 3rd.
Technically, it'd be 2.5, but
Right?
Wait, how did you get to the third? Oh, we're just kidding. No, it's 5 minus 2, buddy.
Okay.
no, because it's in the divide symbol.
Question?
Where'd you get your 2u?
Because we started with these numbers. We broke it into 2 parts. We asked ourselves, what's the biggest number that divides into 16 and 250? And the answer is 2. Right? They're both even, and so.
So the 2u2 is just what you can divide out of
Exactly.
that original problem.
Exactly. But you want to think of it as a number part and a variable part. The variable part's easy. The number part's the hard part. So 2 is the biggest number that divides into both of those. What's the biggest variable that I can divide away from both? The answer is always going to be just the smallest of the powers. So I can, because this one has u to the 5th, but this one only has a u squared to give away, I can only divide away a u squared, right? Okay, so I divide away the u squared, and then the variable's all gone from that second term, right? And the way we get that 125 is just 250 u squared over 2u squared equals that.
Wait, where are you getting the?
Because the 2u squared, that's what I'm factoring out.
That's what we can get rid of initially.
That's what we can divide away. Factoring means
Oh.
dividing. I'm just going to divide that much away from each of those 2 terms, and this is what I'm left over with after I divide it away. Okay? That's all factoring is. You can think of it that way, or just as well, you can think of it as undistributed. They both work, but they mean the same thing mathematically. Okay, so let's keep going with this then. So now we're down to this point right here where we've got 2u squared times 8u cubed minus 125. And just pretend that the reason we're doing this is that we're trying to solve an equation, right? We got to set equal to 0. Now here's how we can think about this. As we factor these great big monsters, certain parts of this we're going to finish, and other parts we're going to have to keep going with. This part is done. Does everybody see that? I'm done factoring. That factor, I can't go any further with that. 2u squared is a monomial. It's done. So if I were solving this equation, all I would have to do with this part is just set it equal to 0. 2u squared equals 0, and what's the solution to that? Divide by 2, so I get u squared equals 0. Square root of 0 is 0. So I'm just going to get u equals 0 from that part, done. Right? Say it again. That is a real solution, you're right. But now look, we've still got this other part over here to deal with, right? This other part is not done. I can't just set that equal to 0 and solve because it's cubed. And here's our rule of thumb. Our rule of thumb is when we're factoring stuff, we have to break it down to the point where the factors are quadratic or smaller. And then we can be done because we can always just set those equal to 0 and solve. The linear ones are easy. The quadratic ones, worst case scenario, quadratic formula, right? Those we can always deal with. But when the factors have cubes in them, we got to keep going. So our rule of thumb is we got to keep going until we get to a point where we have something less than cubes in our factors, right? So this guy we got to keep trudging along with. So let's do that. First one's done. We can just leave that. That one's just going to stay the same the whole time. Okay, but what about this guy? This is what potential pattern?
A plus
hang on.
plus E.
Now we got choices. A squared plus B squared, A squared minus B squared, A cubed plus.
A plus G
A cubed
equals A
plus or
squared
minus
plus AB plus.
This is gonna be, here, let me write them down again. This is important. You gotta pick, these are your 4 available patterns.
It's cute because of the thingy. There's a 3 on it. It's cute.
Which one? Bottom one. The reason the bottom one? Because of that, right? Because the exponent is a cube. So we know this is the winner, but we gotta make it match that. So if we take this guy, this has to turn into something cubed minus something cubed, right? Let's make those blue.
You're crooked.
Okay, so what are my somethings? My A and my B. Now, the question is, what could I cube and get the result 8 times U cubed?
A.
So the variable part is a U,
U.
but what cubed is 8? 2, right? Make sense? Now think in reverse. If I distribute that cubed, I'm going to get 2 cubed times U cubed, which is 8U cubed, yeah. Okay, the number's easy. It's just going to be a cube root of 125, which is 5. Okay, and we'll talk more about those. I'm going to give you a list of perfect squares and perfect cubes that I'm just going to want you to memorize too. Probably a little quiz on it. Easy,
Memorize?
easy, good
What?
grade.
Memorize quiz? You said that really fast. Like it was nothing.
But not today, not today. It'll be like next week.
No
Okay,
one's-
so so let's follow our pattern here then. Now before we move on, let's write the pattern down so we can just plug in, plug and chug. So this is the pattern A cubed minus B cubed equals what?
Equals A cubed.
No,
No, A squared plus minus B.
A minus B.
A minus
First
B.
ones are linear, and then I'm going to get the ones where the exponent's actually
A squared minus. Dang it.
plus
AB.
opposite.
AB
Minus.
minus.
Plus.
Last one's always plus.
Plus.
Okay.
That one.
God, I hate this.
Okay. So there's our pattern. Now we just got to follow our pattern. Here's our A, right? And there's our B. Follow the pattern. Okay, so we're going to get A, which is 2U, agreed?
Mm-hmm.
Minus B, which is 5, times A squared. Well, what's A squared again? Well, let's write it this way first. A squared is going to be the quantity 2U squared.
Oh.
Plus A is U, or 2U, sorry. B is 5, right?
Plus 5 squared. So,
Okay, right?
homie.
So now let's get down to our answer. 2U minus 5. So what is the quantity 2U squared?
4U squared.
I gotta distribute the 2, right? That's the most common mistake people are gonna make on this every year, guaranteed.
Plus 10U.
Is forgetting to distribute that.
Plus
Plus 10U, 2U times 5, plus 5 squared, 25, right? And don't forget the part that was already finished out front, 2U squared.
Oh, snapples. Wait.
So that is now, we would say that is completely factored. Why is it completely factored? Because we've got a term out front that can't go any further, we've got a linear factor here, and we've got an irreducible quadratic that, try as we might, we could never factor because it never does, right? If we're using the difference of cubes pattern, the big factor that comes out of this, the quadratic one, is always done. Just based on the pattern, it makes your work easy. That's done. Okay? Make sense?
Yeah.
Takes a little practice, but I think that's a great place to stop. Okay, and I'll put the assignment up, and you can you can practice this a little bit.
Quiz, test.
Really cool.
Do you want to do an IQ test?